Today we will discuss about discretization of elliptic equation. Prerequisite to this tutorial will be 1. Classification of partial differential equation. What is elliptic, parabolic and hyperbolic equation, and Taylor series expansion. How to find the forward difference, backward difference, and central difference of a partial differential equation by or with the help of Taylor series expansion. So I have already discussed about this in my earlier videos, so you can refer to them. I have given the link in the description. So in case of discretization of elliptic equation, what we do is we discretize this Laplace equation and this equation, as if you had seen my classification of partial differential equation video, then you can understand that this equation, the Laplace equation, is an example of elliptic equation. And for elliptic equation, what we do is we use the central difference method to discretize the double derivative terms. So this is the first double derivative and this is the second double derivative. So to discretize this, we use the central difference formula, which is and to discretize this del square t del y square, we use this one. And now when you add these two, you will get okay. Just put this part here and this part here. So you will get this one. And then you can write that T subscript ij is equals to Ti plus 1j plus Ti minus 1j plus ti comma j plus 1 plus ti comma j minus 1 whole divided by 4. Because here it is minus 4 tij, and if you take this one into the RHS right hand side, then you have 4 tij, then you put 4 in the left hand side in the denominator, so you will get this. And this tij will give the temperature at the ith and jth point. And here the temperature is a function of positional coordinates x and y. Example of this. Here you can say that this is a square plate, although it is not square exactly, but let us assume that this is a square plate of uniform dimension. This side 4 meter, this side 4 meter. And we know what is the edge temperatures. This right hand edge, suppose it has a temperature of 100 degrees centigrade. This downward edge has a temperature of 70 degrees centigrade. And in the right hand edge, we have a temperature of 70 degrees centigrade. And in the upward edge, we have a temperature of say 50 degrees centigrade. Now, what we want to know is what is the temperature inside this square plate. So, as discussed, this is a square plate. So, this is 100 degrees centigrade. This is 70. This is 70. And in the upside, it is 50 degrees centigrade. We want to know what is the internal temperature. And if I assume that this is the origin point, then this side is your x and this side is your y. Now, what we can do is we can divide this square plate into segments of uniform dimension, and we can find the temperature at the junction point of these segments. Now, suppose this is a 4 by 4 plate, 4 meter by 4 meter. And if we assume that del x to be 1 meter and del y to be 1 meter, then we can divide this plate into 16 segments. Each segment of 1 square meter area. And then what will happen is, let us draw the segments. So this is 1, 2, 3, 4 segments. This is 1, 2, 3, 4 segments, and in total 16 segments are there. And 16 segments, so the junction point is this one, this one, this one. So all these are the junction points. And this one, these points are at the edge points. And all these points are known as nodes, where these edge nodes, the temperature at these edge nodes are known, because we know that the temperature at the edge is 70 degrees centigrade in the right hand side, in the downward side also 70 degrees, left hand side 100, and upside 50 degrees centigrade. So if the edge is at this temperature, then all the points at the edge is also in the same temperature. So all these points are in the same temperature. That means all the points, this one, this one, this one are at 70 degrees centigrade. This one, this one, this one, this one is at 70 degrees centigrade. Then this one, this one, this one, is 100 degrees centigrade. So these points where the two edges meet, these are undefined. So actually these are the resultant of the temperature of the two edges. So for now we will ignore these points. These 4 points we can ignore. Okay. So these 4 points we are ignoring, and all the other points, the points which are in the edge, at the edge, they are at the edge temperature. But these points, this point, this point, this point, these 9 nodes or 9 points, we do not know the temperature at these. They are the internal nodes and they represents the internal temperature, which is unknown and can only be find out or can only be found out by discretizing the Laplace equation representing the heat transfer through a square metal plate. The formula, discretized formula is, or the discretized format is already discussed in the initial part. This is equal to Ti plus 1 J plus Ti minus 1 J plus Ti J plus 1 plus Ti J minus 1 equals to Tij, and in the LHS we have to divide it by 4. And what is this Tij? Actually I is at the X direction and J is the Y direction. So in the origin both I and J is 0, and if you go towards this direction at the X direction, then I will change, and when you go in the Y direction, then J will change. So here what happened, this is 0 0, okay, and after then what happens, this is 0 0, and now this point is what, this is in the X direction, that means I will be 1, I will change, but Y will remain as 0. This is 2, Y same, this is 3, Y same, this is 4, Y same at the 0 point. And in this way, when we move towards the Y direction, then what will happen? This is 0, Y1, this is 0, Y2, this is 0, Y3, and this is 0, Y4. Okay, now we have to know what is the point at this point. This is your T. What is the temperature at this point? So this is your T1 by 1. X is 1, Y is 1. But that means I is 1 and J is 1 also. Now we have to find out the temperature at T11 with the help of the temperature at T21 plus T01 plus T1 2 plus T1 0, right? Because we are trying to find out the temperature at 1. So this is T21, T01, because I plus 1 will be 2 if I is equals to 1, and this will be 0. And when J is equals to 1, then J will be 2 here, and on the next point it will be 0. So now let us see what will be our, and this will be divided by 4. So now let us see which are the temperature we know among these 4 temperatures. These are all temperature. So let us see the temperature at 2-1. 2-1 means this point. This temperature we do not know, unknown. And T01 we know. This is the edge point. This is at the edge, and which the edge which is at 100 degrees centigrade temperature. So, and all the points at the edge will be at the same temperature. So this will become this Ti plus, this T01, x is 0 and y is 1. So this will be your 100 degree centigrade, because this is the point. T0 but y is 1. I is 0 but k is 1. So this will be 100 degree centigrade. Again, let us see what is T12. T12 will be this point. This is unknown, correct? So this is unknown. This is unknown T21. This is unknown T12. But do we know what is T10? T10 will be this point. And all these points at this edge is at 70 degree centigrade. So this will be your 70 degree centigrade. So you see T11 will be T21 plus T12 plus 170 degree centigrade divided by 4. So here we have two unknowns, and this is the equation which represents the T1, the temperature at this first point, this one. Then let us move to the next one, this one. This one is at T1. This will be your what will be this one? This point will be T12. So if this is your 0, 1, 2, so this will be your T21. That means this point. So T21, if you find out, you will see that. So T21, here it is T11, right? Because here also it will be I minus 1. So 2 minus 1 is 1. Here will remain as it is. Plus I plus 1 at this point. So this will be your T31. Again, for y cases, this point and this point, you see, this will be your actually T2, 2. This point. This point is your T22 plus T20. 1 minus 1 will be 0. So this will be this point, the H point, whose temperature we know that is at 70 degree centigrade, right? This point is at 70 degree centigrade. But we do not know what is T11. We do not know what is T31. We do not know what is T22. That means we do not know this point, we do not know this point, we do not know this point. Although T11 in the earlier step we have calculated to be this one, this part. And you can put it here. Now similarly, you have, if you try to find out the temperature at this point, that means we have calculated T11, then T21. Now you calculate T31. There also you will find an equation with some values available, but some values are not available. In this way, if you move like this, Then you will find 9 equations with 9 unknowns. So 9 equations, 9 unknowns. So you can solve it by the binary solution method or the equation solving method, and then you can find the values of these 9 unknowns. And then you get also to know what is the values of the internal node of the square plate. Here, as you can see, there will be 9 equations when you try to find out the temperature at each of the internal node with 9 unknowns, right? So you have to solve all those 9 equations to find the value of the 9 unknowns. So this method is known as direct method. Direct method of discretizing the elliptic PDE, which represent here in this case, this example, it is representing the temperature distribution in the internal area of a square metal plate. If all the edge temperature is known, then you will have this case 9 unknown, 9 equation. Solve all the unknown, solve the equations for this 9 unknown, and you will get the temperature at all these intervals, right? And this method is known as direct method. This is not an iterative method. It requires solving 9 equations. Now, in the previous slide, I was talking about the direct method of finding the internal temperature of at the 9 nodes inside the square metal plate. This is 100, this is 70, this is 70, this is 50. And we have divided it into 16 segments of equal dimension, where x and y is at 1 meter. This here. So we want to know what is this, what is this, what is this. And in the direct method, what we have found is, we have found 9 equations with 9 unknowns. And I have said when you solve this 9 equation, you will get the value of 9 unknowns. So there is some error will be there, because first of all, this is a one of a method, one step method, not a iterative method. And as you know, the equations can be solved and values can change. So in case of binary equations or any other equation solving method, there can be multiple solutions, right? So we do not know which one will be the most accurate. That is why what we do is we devise the iterative methods known as Gauss-Seidel-Mann method. And what this method does is, it follows the same practice that is followed in the direct method. So here also what we do is, first of all we'll try to find out the T11. So T11, as you know, 11 will be equals to I plus 1. So 21 plus I minus 1, T01 plus T12 plus T10, as I said, I plus 1 here, I minus 1 here, J plus 1 here, J plus 1 here, J minus 1 here, because I is the X and J is the Y, and this entire expression will be divided by 4. So if you observe this now, as I have already discussed in the previous method, you'll see that we to find out the temperature at this point, we need the temperature at this point, this point, this point, and this point. Where the point at this part and this part is known because they are at the edge. So all the points on the edge will have the same temperature. So T01, that is this point, will be at 100 degrees centigrade, and T10 will be at 70 degrees centigrade, correct? Because this edge is at 100 degrees centigrade and this edge is at 70 degrees centigrade. So the unknowns are these two. So now in Gauss-Lieberman method, we assume that all the internal nodes are at 20 degrees centigrade. Sorry, this is not correct. We assume that all the temperature at all the internal nodes is at 0 degrees centigrade. So we can assume that this T21 is at 0 degrees centigrade and T12 is at 0 degrees centigrade. So T11 will be 100 plus 70, 170 degrees centigrade. So this 170 degrees centigrade will be the temperature of this point. If we assume that all the internal nodes are at 0, that means all these nodes are at 0. But the nodes on the edge, at the edge, will have the temperature of the edge. Okay, here also. Then we go to this point, T, what is this? 21. So in case of T21, you see the value says that T21 is T31 I plus 1 plus I minus 1, that means T11. And then we go for J plus 1, that means this will be your 22 plus J minus 1, that means this will be your 2, 2, 0, correct? So this T31 is this point. This is at 0 degrees centigrade. T11 we have calculated to be 170 degrees centigrade. T22 so here I am doing this. T22 will be this point and T31 will be this point. I'm sorry. This is T31 and this is T22. Correct? So this T22 will be also at 0 degrees centigrade because these are all actually unknown internal nodes. And T20 will be at this edge temperature, T20. This is your T20. So this will be at the edge temperature, which is 70 degrees centigrade. So if we sum up, we'll have one thing is here T11 will be 170 by 4. So here also we have to use 170 by 4. So T21 will be 0 plus 0, 170 degree by 4 plus, what is this, 70 degree, 70 degree all through the division by 4. Correct? So these will be, actually 42.5. Correct? So T21 will be around 112.5 degrees centigrade divided by 4. So T21 will be 112.5 degrees centigrade by 4, which will be again your 0.125 like this. Yep. Right? And in the similar manner, you can find out what is the temperature here. Then you again move to this. As I have said, the movement will be like this, like this, like this. So you see, you will find the value of this, then this, right? And now you can see that after the first iteration is completed, then you will find that here in the T1, this point actually we have assumed to be 0 degrees centigrade. But it has come up to be, after iteration, it was found that it is not 0, but it is 42.5 degrees centigrade. So what is the error or what is the difference? So presently, what we have found out after first iteration, we have found out that this T11 is actually the T11 is 42.5 degrees centigrade. But originally we have assumed that all the internal nodes stays at 0 degrees centigrade. So now if you use this equation, you will find the error or the relative absolute error of the iteration, the first iteration. Correct? So you can find it in the percentage by multiplying it by 100, sorry, not 100, but only 100, right? So this will give you your percentage RAE, relative absolute error. Now your goal will be at each iteration, your goal will be to reduce, to minimize this relative absolute error at least less than 20 degrees centigrade. Sorry, again I am mistaken, it is 20%. At least less than 20%. So what will happen is, in the second iteration, you will again try to find out the values of temperature at 1 node, this 1 node, 2 node, and so on, 2 node, then 3 node, then 4 node, then sorry, this will not be 4 this will be 1 2, correct? Because this is your 0 point, this is the origin. After then this will be your what? X is 0, x is 1, y is 0, x is 2, y is 0, x is 3, y is 0, and this is your 4, y is 0, right? This point will be 1 1, matlab x is 1, y is 1, because this point. So this is 1 1, this is 2 1, this is 3 1, this is 4 1. Then you move to that point, this will be your 1 2, 2 2, 3 2, 4 2. Then move into this point, this will be your 1 3, 2 3, 3 3, 4 3. Then this will be your 1 4, 2 4, 3 4, 4 4. These are all coordinates, spatial coordinates. And this is this is will be 0, 4, this will be 0, 3, this will be 0, 2, this will be 0, 1, right? So in the next iteration, what you will do, you will try to find out the temperature at this point, this point, this point, then this point, this point, this point, then this point, this point, this point again. And again you will get a new T11, right? New 2 T21 and so on. So then again what you will do is you will again apply this equation to find out the relative absolute error. So the formula of this relative absolute error is T present minus T previous T present. So T present means at the beginning of the iteration, what is the temperature that you know? And T previous means what was the temperature at the previous iteration. So if there are 3 iterations, suppose 0th iteration, then first, second, if there are 3 iterations, then at this case, what will happen? To find out the error is the T at 1 minus T at 0 divided by T at 1, because T at 2 you do not know. Sorry, there is a mistake again. So this will be your T2, then T1, then T1. Is it correct? No. So the correct form is relative. So the formula of relative absolute error is T present, T previous, T present. This T present means the present iteration. After calculating the temperature of the present iteration, what is the T present? What was the previous? What was the T at previous? Divided by T present. That means if you are in the first 2, 3, 4, then T present at the 4th iteration will be the temperature you have found out after iterating for the 4th time, minus temperature at the previous iteration, this one. Then you divide it by T4 again. So T present means what was the temperature after you have calculated the temperature at each of the internal node at the present iteration. So, and the previous iteration will certainly be the previous iteration. In this case, after the 4th iteration, you have found out the temperature T4. Now you minus T3, this was the temperature in the previous iteration. And then you divided it by the present temperature again, the temperature at the present after you have computed the present iteration. And then you mod it, that means absolute, take the absolute value and multiply it by 100. So it will give the percentage relative absolute error. And when this error is less than 20%, you stop the iteration. Or if you want, you can go for a more accurate difference. So let us say less than 5% or even less than 1%. More you will go for accuracy, more iterations will be required, more computational energy will be lost, and also it will be cost more because you have to run the iterations in a computational framework. But yes, you can expect a higher accuracy. And if you want to save money, if you want to save cost, if you want to save your computational power, then you go stick with this 20%. So this is overall the Gauss-Lieberman method. So as you can see that in case of direct method, you have to solve the 9 equations to find the 9 unknowns. Now, the problem with this is, as you know, this binary equation or any equation solving method uh, has multiple solutions, and any one solution will be given after the calculation of the binary equation or any equation solving method. But in this case, in this direct method, you have no scope to analyze the error, this relative absolute error. But in case of Gauss-Seidel method, as it is the iterative method, so you can analyze the RAE, relative absolute error, and accordingly you move ahead for a better solution, right? So this is the basic difference between the direct method and the Gauss-Seidel method, where direct method is a non-iterative method, and the Gauss-Seidel method is a iterative method. The direct method is a non-iterative method, and Gauss-Seidel method is an iterative method. So chance of improvement is more in case of Gauss-Seidel method, chance of improved solution or chance of achieving improved solution is more in case of Gauss-Seidel method compared to the direct method. So in the next video, I will discuss about another discretization method of elliptic PDEs. This will be your Lieberman method. And in case of Lieberman method, this Lieberman method is also an iterative method, but with an improvement compared to the Gauss-Seidel